n dimensions, one can relate the two problems, the two hierarchies by high dimensional inflation. Which, okay, I don't go through because of time, but I can leave it in the transparency slides. Now the next question is that this is static, but we can relate the two observations that high dimensional inflation can relate this, can keep extra dimensions large size and can relate particle physics in the closed hierarchy. The next question is if we can find a high dimensional inflation, like high dimensional inflation, it's possible also to produce the primordial fluctuations that are observed in CMB. So this is what I will discuss now. So before that, let me mention that the physical distance in the different dimensions is different because the scale factor is different. So the problem time is different. So in if I start with a moving distance between two spaces, let me points in the space, then I have to multiply the scale factor A in order to find the physical distance. And since A, the four-dimensional scale factor and the five-dimensional scale factor are not the same, but they are related to half, then one finds that the five-dimensional proper distance is, sorry, the four-dimensional proper distance is the five-dimensional proper distance times this factor of the radius to the final value of the initial value. But when you translate it into units, this is just the change of units. So it is multiplied by the ratio of the Planck mass in 4 dimensions divided by the Planck mass in high dimensions. So just the change of units. So this was a parenthesis. It's important because now what we can do is we have the CFD data, which are very precise at shorter distances, shorter than about 10 degrees in the sky. So in the there you see that at the lower L or higher angular distances, there are big errors, while on the right side of the curve there are no errors. In distance, this corresponds to gigaparsec today or megaparsec at the time of the CFD. And now you can take this distance and extrapolate back in the past up to the inflation scale. So if you go to the TV, then this was done properly fast. Then you find that the megaparsec becomes million of kilometers. So if you take now for TV, to do things, let's multiply by TV of and second, convert the units from 4 dimensions to 5 dimensions. So much multiply by this number. So if I take the scale of relation to be of the order of 5 dimensions, the graph scale in the stars or the scale of the order, then find us the factor which is TV over a Planck. TV over a Planck is 10 to the minus 14, and TV to the kilometers the micro scale. So this is another coincidence which tells you that if high-dimensional inflation can produce fluctuations, then there would be a deviation at the distance, which is minus scale in the past, and it's more exposed around 10 degrees in the sky, which is consistent with the data. So this is an accidental, let's say, nice coincidence, which now can be solved and works. So there is an approach is the following that one way we describe the reflection is inflator, which is in 5 dimensions. 5 dimensional field. It's just a flat region at some point, at some region with its potential. Along that flat region, you have inflation, so the field, the reflector behaves during inflation like masses during the in the space with the cosmological constant, so in the zeta space. Then such a masses fit in the space as the property as a two-point function that belongs to the elliptical in the distance. Or if you want the momentum space, the fluctuations constant. So the equal time correlation in momentum space of this field of the equal field when you go forward in time, how and the performance times then the behavior goes like to the force in 4 dimensions, or 1 over k cube in 4 dimensions. The k, put k hat, k hat square is k square, which is the momentum square, plus the extra component of the momentum, which is n square over r square. Since the standard model is on the plane, or if you want, you don't observe the excitation, just to sum the all of them. And then it finds that this expression is functions. And this has the following behavior. If you look at the momentum in some lines, therefore small distances, compare then when it happens a scaling variance spectrum, the amplitude goes like a constant, like a while if you look at small vectors, then you find same behavior, which is behavior from 5 dimensions, so you have more power spectrum at lower multiple moments, which make the spectral index from 1 to 0. So this property is important in order to find it. One has to treat the integral 5 dimensional field with a summation. So it's like if the primordial fluctuations are produced not only by the zero mode of the integral, for the measure zero mode, but also and if one normalizes the approximation, we normalize the prediction to the lower time moments, then one can compare the prediction to 4 dimensional which is solar line, to the kind of dimensional inflation, 5 dimensional which is 1 over k. This gives more power spectrum. So this is in principle if the errors are same, but if the errors are reduced in the future, at least in some region, we will take there is only one universal say, but in the region around 10, maybe more, the region could be the errors could be reduced, in which case one can test this prediction. So I didn't mention before. One can do these calculations that I justified before properly by introducing also the slower parameters. One can find all the spectrum calculations. So addition to the integral, you have the five-dimensional diagram. The five-dimensional diagram is five polarizations. Two correspond to the four-dimensional one. One is an extra scalar, which is what is and the zero mode of the vector is projected out of this plane, so move out the. So in principle, there is a two scalars, that the scalar second scalar that this contribution is suppressed by explorer parameters, like because it comes from the graviton, exactly like in four dimensions, that the B modes are suppressed. So the method just happen at the end of the equation. So at the end of the equation, the reference already has an answer. So the equation, the five dimensional equation goes to some minimum. It creates oscillates some minimum. And then it creates particles. These particles can be either particles from the brain, by introducing the coupling of the influence, or in the particles of the gravity. So depending on the mass of the electron, the big predominantly to start gravity. Also, if the potential at the minimum of the electron has a non-zero positive value, then this gives rise to the potential for the radial, which will continue to so this one of the one potentials can be either can be with tensors, because translate canonical normalization, then an exponent which is 0.8, which is the tensors. However, it can also be stabilized with this way by adding extra tensors, which is the can come for instance the tension of the or the and depending on parameters there, then can up to very large uh, electron volt square. An interesting possibility is that radiation run away from stabilized with the Hansen energy. Behaves like one of the atoms. And it's positive for fermions and negative for bosons. So this is the one where potential it goes up. At some point, due to the Hansen energy, due to the fact that the contribution of the particles, the five dimensional particles is five realizations, then it goes down, that is a maximum. But you can understand it's like the light field is which gets the pass, then it can create local which can have also cosmological constant. So for these values, it's positive. It can stabilize the radius. Actually, yeah, I would like to finish for this case. There was a way model that was proposed to account for the cost of the having tensions parameter, which is lower than is measured by CMD, by the calculator, and it is higher for today, lower observations. And, there is a proposal that lambda comes the exact design around the electricity which is around equal to, then this will explain the density. Also, so the of course the cosmological same sign in the season there is always problems season factor are usually distance in one space. This transition to happen quantum time if there is in, as I said in the utilization by the customer of the electrics, if there is a scalar, this usually it has a mass, it has two minima, also being two minimum. In the false minimum, the mass comes from the disaster, the battery is at the center, while the true minimum doesn't come, and then the minimum changes to the center. So this is the last point. So that's my go to the conclusions. There are too many things. Points that are important. The second is that the smallness of physical parameters could be a signal that we live at a large distance further in the landscape vacuum. It is something that can stay. With microscopic size that maximum which has been technology about the zero mass cosmology and maximum. The second part extra dimensions can apply to size from the type dimension prediction by connecting the difference of the universe. This in particular it works in 5 dimensions.
Thank you very much for your excellent presentation. Any question?
Thank you very much for the presentation. Forgive me, but I'd like to make a comment as much and then a question maybe following. So at the beginning of your talk, you showed the effect of higher dimension stuff and scaling with dimensionality proportional to 1 over e minus 2. Thank you. Okay, sorry, 1 over d plus 2. So my understanding is that one can derive this somewhat heuristically by considering where if you have an MR diagram or mass radius diagram, you consider where the quantum radius line intersects the Schwarzschild line. The Schwarzschild line is dimension independent. This is correct?
Yeah, you can do it like this, but I think the easiest way to do it is you start from a high dimension and multiply 4, so you multiply with the volume. So
yeah. Yeah. So this effectively assumes that volumes or radii are changing with dimensionality, but the quantum line is dimensionally independent. It's always one over.
yeah, for the volume you have to say how many where to start, how many extra dimensions.
Yeah, so for the volume that's fine, but in order to get this ending with the effect, high-dimensional time scale, you need a dimensionally independent quantum scale and a dimensionally
No, no, that's not. Fix the number of dimensions. So you start from 5 plus d, and you go to 4. the three extra dimensions at the same time. The power.
But you would still have the same.
Twice.
But in all these dimensionalities, you would always have a quantum scale.
Same stuff. The unit is
Yes, but you would always have a material quantum particle. You would have a quantum scale. Goes like a memory. So this is one way to think about it. But if one uses a very heuristic argument, it is heuristic energy of a particle, including the rest matter component minus gravitational energy. And it's very easy to get a scaling where there's a dimensional dependence in the quantum scale. And when one does that, at the same time, we introduce symmetry in the MR diagram, which means that your effective energy scale is always the usual quantum mass, and it doesn't have this kind of star. In this case, what it basically means is if it's like you could have even micron scale dimension. You never see it. You know way to Okay, maybe I can talk you through it.
So we have a very brief question. What is the interaction concept between normal method and the dark method? The interaction cross-section between method, between ordinary method.
what counts, I didn't mention about to make it bounce, you only need to study the so that you follow high dimension.
It's a normal method moving around galaxies in the
Of course, yeah,
Is there any interaction cross-section which could be observable?
are you mean for 5 dimensions, but you want to go
Yes.
yeah, the difficult studies that more smaller but more accelerated in the past extra dimensions involved with TV side. These are not heavy as well.
Thank you. I also have a really short question. So at some point, I think you mentioned that there are no exact global symmetries in nature. You maybe clarify what you mean by exact. True, then it refers to the apply and not any construct quantities whatsoever. We could apply any other percent theorem which gives us compression equations. But if this is true that there are no exact global symmetries, then we don't have any constant quantities.
The electromagnetic side global impact. Then you imply that the black holes evaluate the violate any global particular value.
Thank you. Last question. There's another brief question. Do you have a prediction for primordial
With the gray body factor, that no, we have to do that. The only computation we did was if you get the orbit level of the dark matter from the take into account the correct further measures. In principle, you can do that. Yes, the saturation the open is in the difference. The other uh, the upper line here corresponds to 100%. Right, so by molecular force to be 100%.
That's another gap of this more to the last talk will be given by Steve. You have 15 minutes. Mr. Stephen Ross will speak about legs,
This is your
quadrature of the set from University College of London.
Yes, I can move it down.
Yes, you can move now, and you can steer. Yes, must push. This is the laser point.
Which is the laser pointer?
No, 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 no.
Brilliant.
And then you block. So this one, the first.
Yeah.
Yeah, yeah.
Perfect.
That's the laser. And you can do control in this way.
Yeah, absolutely. Good morning, everyone. So today's talk is about a rather arcane topic, namely squaring the circle. This, of course, goes back to the ancient Greeks. The problem, as conceived by them, was to draw a side of a square equal in area to a given circle. The problem is first mentioned in connection with the Greek philosopher Anaxagoras, who apparently considered this while in prison or in piety. The very difficulty of the problem inspired a lot of interesting mathematical innovations, such as, for example, new methods, for example, the method of exhaustion, and new curves, such as the spiral. And both of these can be seen in the work of Archimedes. So, in the measurement of a circle, Archimedes used the method of exhaustion, inscribing and circumscribing regular polygons around the circle to show that the area of the circle is equal to the right angle triangle, where the sides of the right angle are equal respectively to the radius and the circumference of the circle. Of course, this doesn't count as quadrature, so you can certainly draw the height of that triangle equal to the radius. It's not clear how you rectify the circumference of the circle in order to be able to draw the base. Another interesting idea is actually using a new curve. So Archimedes actually invented the spiral for the purpose of the quadrature. So he showed that the subtangent there, OT, is equal to the circumference of the circle. The spiral is completed one revolution. And the hypotenuse of that triangle is drawn tangent to the spiral at the point of its first revolution. And so, like the previous theorem, you've got there a triangle where one side is equal to radius, and subtangent OT is equal to the circumference, and therefore the triangle will be exactly equal to the area of the first circle. But of course, that doesn't count as a classical quadrature either, because of course you solve the problem of rectifying the circumference, but it's not clear how just using straight edge and compass, which are the only allowable tools, you can actually draw a spiral, a tangent to the spiral. So it seems that the Greeks themselves considered the problem quite notorious in Japanese as square ended a ludicrous character, and since then squaring a circle has become quite an impossible task, only attempted by cranks. Of course, the reason that, at least in the context of Euclidean geometry, the quadrature of the circle is impossible is that the square of the circle you need to draw a side equal to root pi. And the only constructed lengths are lengths which are algebraic numbers, in particular the root of a polynomial equation with intercoefficients whose degree equals a power 2. That was shown by Ansel in the 19th century, and then later on, von Lindemann showed that pi is not an algebraic number but a transcendental number, and therefore it seemed that von Lindemann had a whole problem to fix the quadrature of the circle is impossible. However, this is only in the context of Euclidean geometry. But in 1832, Polyai, in his Absolute Science of Space, which he published as an appendix to his father's textbook, showed that in the context of hyperbolic geometry, Euclid's first four postulates are retained, but the postulate is replaced by a different axiom, namely through a point more than one line can be drawn parallel to the line. In these circumstances, it is possible to square some circles. Janusz Wojtyła was immensely proud of his achievement for he actually mentions it on the title page of his appendix. And indeed, this attempt at the quadrature of the circle is not to be found in the writings of the other two people associated with non-Euclidean geometry, Lobachevsky and Gauss. It's just Polyai's. How is it possible? Well, it's possible because of the fact that in hyperbolic geometry, both the circle and the square are functions of pi, and therefore the quantity pi cancels out, which avoids the need for trying to construct. Why is this? Well, the curious bit is the fact that the square is a function of pi. In actual fact, what I showed that the area of any convex polygon is equal to its defect times k squared. The defect being, of course, the amount of which its angle sum falls short of the Euclidean value, and k being this mysterious ubiquitous constant in hyperbolic geometry. So, in the case of a square, of course, squares don't exist in hyperbolic geometry, but in the case of an equilateral equal acute angles magnitude W, the area of such a square would be 2 pi minus 4w times k squared. And in the case of angles lambda mu, then by the same token, its area would be pi minus sum of those angles times k squared. What I took triangle. The triangle of maximum size. This is a triangle whose sides are asymptotically its vertices line at points of infinity, so its angle sum is going to be 0, and therefore its defect will be the maximum defect, which is pi. And so the extraordinary fact is that the area of this triangle of maximum size is given by pi k squared. Okay, so we've got the linear figure. Just 5 minutes, wow. They go faster than hand. So we now need to think about a circle. Well, Bonnier actually developed a very curious angle formula for the area of a circle, which is that the area is given by pi k squared times tan squared z. And this z is the unique acute angle associated with every circle of a given radius. So you can see that tan squared z is a sort of scaling factor which expresses the ratio of the area of the circle to the triangle maximum size. And that's then the key to the quadratic. So, to achieve the quadrature, you've got to do two things. First, find the ratio of your circle to the maximum triangle, and then draw a square equal to the maximum triangle. Bonnier provided a construction to obtain the angle z, which corresponds to a certain radius. But in practice, it's easier to work the other way around, is to find a nice constructible z, and then work out the radius. And that can also be done. If, for example, you take a circle whose associated angle z is 45 degrees, then tan squared z is 1. So the ratio of such a circle to the maximum triangle would be equality. And that's the one that Bonnier chose. So then, his task was to construct a square equal in area to the maximum triangle. And you can see that square there. The internal angle will be 45 degrees, and so angle OA will be half of that. And the angle at the center will be 45 degrees. So to construct that square, we just need 8 copies of triangle OAN. The angle is not going to be a problem because those angles can be constructed with compass and straight edge simply by using Euclid's theorem on bisecting angles. The problem is getting a sine. How do we get angle sine A? In order to do that, Bonnier used one of his identities of a right angle triangle in the hyperbolic plane, where a side can be expressed in terms of angles. So what we're looking for is side A, and we find that according to this formula, the hyperbolic cosine of A over K is equal to the cosine divided by the sine of the two acute angles. And now, that doesn't look very promising. It seems that if you wanted to get side A, you first of all want to construct the equation of two sines, doable. You then got to construct the inverse hyperbolic Cohen's cosine. I'm not sure about that. I don't think that can be done. And then you have to multiply it by k, this ubiquitous constant whose value is unknown, and that is absolutely impossible. But of course, Body was not going to go that route. Neither was his commentator Bonola, who came up with a nice way of sorting this problem out. And the way to do it is actually to express those angles as if they were angles of parallelism, and to express them in terms of the corresponding set to a given angle of parallelism. So that rather odd equation, hyperbolic cosine of A over K, has sine of an angle of parallelism divided by the sine of another angle of parallelism, where corresponding segments of E dash and C dash. At this point, Bonola invoked the fundamental identity of hyperbolic geometry to express those angles in terms of size. And was able to obtain that equation there. Of course, that's not much use to us because we now have to actually draw B dash and C dash, but in fact, we'll provide the instruction to do that. And then all that we have to do is to draw an auxiliary right angle triangle whose sides B dash and C dash. One of the identities of the hyperbolic plane will mean that that equation 3 is true. When you compare that equation to the previous equation, you see that A dash is equal to A. In other words, the third side of this constructible right angle triangle is actually equal to the side of the triangle inside that square. And therefore, the construction is possible. What I noticed is that, okay, it's possible to obtain the quadrature of one circle where the associated angles are 5 degrees. Notice that it can be done in general by providing tan squared instead. It's either an integer or a rational number where the denominator is 2 to the n times various distinct Fermat primes. That's not one. Okay, thank you very much.
Thank you very much for the excellent presentation. It was okay. Now, question started yeah, all our speakers this morning, and this session is closed. We have to go to lunch, and at the one, please be available if you want to join. This is important. Yes, at 14, 13 plus 14. Okay.
I can put my presentation.
Yeah, you have it on USB or on the laptop? Is it on your
No,
laptop?
it would be better
from
to
my own.
download here, to use only one laptop for all presentations. Then
Do you have a USB?
Here? Yes.
Yes, but
no, no,
the
do
stick.
you have a stick? Memory stick.
No, I can send to email or
Email,
By email, yes, but there is no internet.
you have internet.
Yeah, here there is internet.
it's
Okay.
your own laptop.
No, yeah, it is.
It is my laptop, but uh, uh, if you have a
Oh, I
memory
can
stick,
with
no,
my
no,
own
no,
laptop.
no. Do you have a memory stick? Because we can copy from this computer on the memory. We can.
Can I
Anyway,
talk on my own laptop or you put it here?
it is up to you. After all,
Okay.
Is it possible
you
to
can.
use full screen mode?
It is possible to use full screen.
Because it's smaller than voice prompt.
It's possible to use full screen mode. If you have a
Yes,
PDF,
So maybe I
you
come a
just-
bit
you
10
can't
minutes
really
before the
present
talk
Yes,
to set
and-
it maybe
yes,
on my
yes,
own
This
laptop.
was not
Yes, you can use your own laptop. Doesn't matter.
Could this one, yeah, it's the full screen.
So should we go get a memory stick?
Yes, 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 yes. The memory
My
stick, and
presentation will be in the evening.
or you can use your computer. It's up to you. Okay, maybe yes. It's your talk is not the.
It's in the evening.
Is the evening.
Yes.
Yes, yes, yes. So there is still
Who
time.
is
We will.
next?
Professor Shafielu, the gentleman just left. Bun, el este vrea la calculatorul lui, atunci și eu cam Deci de comentez
Cu
asta
sunetul nu
și-
știu dacă se poate face ceva
Nu
mai
se
bine
poate,
de atât,
atunci
dacă
lăsăm
ăsta
așa.
îi
Lăsăm
așa.
așa, important este să ne
Să se audă.
concentrăm pe succesul conferinței, care să se audă bine. Să se auzit bine.
Da, da, e ăsta. Sunetul ăsta, buzuitul ăsta care mă enervează, dar cred că nu se poate, efectiv e interferența de radio din jur. Deci, asta tot pe radio. Și dacă
Good,
orice
good,
frecvență prinde, radio
Știu.
o ia.
Așa este. Bun, deci Shafielu își va aduce calculatorul cu 10 minute înainte.
Atunci rămâne așa prezentare, pauză și la live stream.
Yes. My talk. Use your computer. Yes. Just put here your computer.
Okay, so now as for the application of the installed validation, Then, like, of the state and they claim that person had for a record leaving some of the properties.
Which group you are talking about? Okay. So, my quick answer is that there are loads of claims, and I'm not saying that they are all wrong, but many of them are not really well verified, justified, or well studied. As I said, people have been writing papers on my model to solve the problem, and I have to say that no, it's not. But the point is that many of the papers that people try to solve something, what they do, they find a particular combination of the data. I'm not saying it is intentional, but they find a particular combination of the data that the particular model which the scenario they are studying solve the problem. But what we call about the Hubble tension to resolve everything is that some of the main data, and what I say by main data, I mean the data that the majority of the physical cosmologists agree on the reliability. Talk about the customer background, let's say from talk about the Baranaka speculation from Berkeley or DESI or STSS. Talk about the supernova compilation from the like the DES group or from the Union group or from the Panzon group. So these three are the main data that we are considering. And then, of course, you have the shoes of F0 at the low edge. So there is no model which I can fit all these together in a proper way. But if you just use CMB and shoes and VAO, yes, there are. If you use some particular combination, when we go now beyond FLRW, then things are fundamentally different. Even the data that we use for the growth of a structure is not reliable. The data that we use for growth of a structure is based on the isotopy, even GR. So this is a very common thing. It's not completely correct that people test molecular gravity based on the data which is based on the GR. Or testing things based on the cosmology, which the assumption of the is there, and then we try to test something. So I'm not saying that all these works are wrong, but I'm saying that to make sure they are correct, it's difficult. I mean, one has to spend really large amount of time to evaluate. That's why someone like me, we usually try not to make any. I know you from my bachelor. Thank you, friends. Okay.
But without this leader, partners, mentioned
No, I mean, it's a very good question. First, I never use this type of all questions are good. But this is a very relevant question from the last. First of all, about George, exactly. I have huge respect for him. But yeah, not everything he said is 100%. For example, he was criticizing the super we don't need to take sides. Really complicated. Super so many different small details. I don't know. I think what is that's why I said that we were very careful to use the word quantified. We are not saying the dark energy is evolving. Hints for dark energy. So it might not be 2.6 sigma, it might not be, but it is maybe 2.1. So this is a hint of evolution. And yes, there might be systematic. We have three supernova compilations. We have DESI, and then we use also DESI with the part of the STAR, not only and then with the CME, we use different CME not the one by one, but also the one all of them hints towards a similar behavior. So of course the significance is not yet more than right? But it is very simple. Which so a big part of my talk, actually the whole work of my PhD students was to say that these results are not based on only the, where is it going? So this paper is mainly to use non-parametric methods. As I said, I got to know Eric Nader or David Collarson because I was criticizing. So this parametric form may not work all the time, but these results are based on non-parametric analysis. These Gaussian processes, Gaussian statistics. So they show the similar behavior. So CPLWWA is not working always well, but for this particular behavior issue of non-parametric method needs to work similar. Of course, the significance is not as high as the parametric forms. You see, it might be just like a edge of, but the overall behavior seems to be. So my argument, I have been or yeah, let's wait. Let's wait. That's why we are very careful. But I don't mind to hint to point the we see the hint. If data really suggests that, find out if it's the systematic. So something very important to remember here. When you use non-parametric your contours with your band become large, but it is more reliable in the sense that it allows more flexibility. For example, showed in one of the previous results. So this is for basic 2024, but still 2025 is a similar thing. We see such a behavior exists. Still, you may say, okay, if it's constant, it will still reasonably okay. Right? So non-parametric methods usually give you a hint if they suggest you a particular behavior. In the parametric form, you are using, for example, 2 degrees of freedom, you get this beautiful band of which can indeed be biased because you're forcing a particular behavior to the phenomenon that shows. So non-parametric methods usually is used to validate, to say that, okay, if the behavior which we see, sometimes they can be very contradictory. That's what I showed in some of the previous results, that sometimes it can be really like this one, sometimes it is really wrong. Here I'm using the same parametric form, but for this particular behavior, this behavior is completely wrong. Cross the by line. But for what you observed today, for DESI, compilation CME, the results from the non-parametric and the CPL basically consistent. It cannot be always the case. Maybe God created the universe, but for this universe that we are living, it will be consistent.
Thank you, Arman. Okay, okay,
Can I use this adapter?
Can he use your adapter? Oh, my adapter.
Yeah,
Yes,
yeah,
this
yeah.
one.
Because I think mine
10
is not.
euro.
Okay, I'll give it afterwards.
Okay. Sure, sure. I mean, this is
Thank you.
signal from your computer.
I don't think so because
If it
let me
doesn't work,
change
you can change the
ports.
computer, and I have it USB for audio.
My computer. You do that because then
Yeah,
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 and
yeah.
USB.
I don't have it.
Work hopefully. How do you eject this on Mac?
No worries, I can. I'm really sorry.
No, no,
Don't worry,
worry.
don't worry.
It
It
usually
always
works.
happens. Especially with converters like this, they don't always work. You can keep. Oh,
Not really necessary. Yeah.
you
There
said
is
this
a-
one as well.
The desktop in the desktop.
Desktop then.
Open, just open it.
Yes. Can you full screen or something? presentation. Good luck. You need a microphone, you have it there.
Thank you, thank you.
Okay, let's begin. I invite Miguel Pinto. Please begin. Prepare 15 minutes.
Can you hear me well? Because I don't want to be nervous. Okay, so thank you very much for having me today. I present my called the Lambda CDM-like evolution in Einstein's Taylor Gaussian equation, which was done in collaboration with one of my co-supervisors, in this case. So in order to ensure everyone starts on the exact same page, let us start from the very beginning. As we all know, apart from the incredible revolution general relativity brought us back in 1950, today the Einstein's theory is at the core of the so-called Lambda CDM model, the standard model of cosmology, as we use it to describe gravity at very large cosmological scales. In such a universe, the universe itself is modeled by the Friedman, the method Robertson-Walker metric. That is, we assume that the universe is both homogeneous and isotropic at very large cosmological scales. And in terms of matter content, we assume that we have radiation and baryonic matter, which are very well understood, and two additional dark components, a cosmological constant, which is a basic form for a dark energy component, and cold dark matter. And although these models and theories, that is, lambda CDM and general relativity, are great, they have nonetheless some shortcomings. For example, lambda CDM itself does not explain the true nature of both dark matter and dark energy. We just assume that these are two components in order to match with the observations. In addition, we have the so-called Hubble tension, that is a discrepancy between early time and late time measurements of the exact same quantity, the present value of the Hubble constant. And on the more theoretical side, it has been demonstrated that GR lacks uniqueness in the sense that there are other alternative theories that can explain the exact same phenomena as GR, but by resorting to other geometrical quantities, in particular torsion and non-metricity. So are these problems hints that new physics is needed? Perhaps. And one possible path to do so is to assume that it is possible to modify gravity. It's possible to assume that GR, even at cosmological scales, is not the final theory. So here we have some physical motivations for such modifications of gravity. To first explain the dark components of the universe, dark energy and dark matter. In addition, to deal with the theoretical issues of GR, for example, the question of its non-renormalizability, and to provide a more realistic representation of the gravitational fields near curvature singularities. As a consequence, to set a viable framework for the possible quantization of the gravitational interaction. And how does one modify gravity? Well, according to Lovelock's theorem, one can do essentially four things. One can add extra fields to the gravitational sector, add more than second-order derivatives of the metric. This happens, for example, in theories, include non-locality, and add extra dimensions. And this is the recipe for doing modified gravity. Here is simply a roadmap or sketch for the existing modified gravity theories. I will, in particular, delve into the so-called Einstein scalar gravity. This theory has been gaining some attention in the last couple of years due to some particular reasons. The first one is that it contains the Gauss-von net term, which is the first non-trivial higher curvature correction to the Einstein-Hilbert action, that is the action of general relativity, leading to second-order field equations. Furthermore, it's inspired by fundamental physics in the sense that this coupling between the Gauss-von net gravity and the scalar field arises in the low energy expansion of specific string theories. Moreover, it's a self-consistent theory in the sense that it is free from Ostrogradsky and Laplacian instabilities, as it is part of the Orn-Densky class. This does not mean that the theory does not contain tachyonic instabilities, but that's a whole new and another subject. And finally, it has some rich phenomenology. It contains a unified Laplace solutions with So in my case, I am motivated to explore these context. I'm trying to set, formulate an exotic compact object and compare the simulations from these objects with observational. And, however, one may ask first if this theory admits a lambda CDM like evolution, which is pretty much like lambda CDM models, but without introducing pathologies in the scalar field itself and of the right after this slide. So here are the steps for this work. First, we will explore the space without assuming anything apart from geometry and the matter distribution. Then we will perform a dynamical reconstruction of the lambda CDM model, assuming a spatially flat universe. We will consider the lambda CDM model solutions and introduce them back into our dynamical system. Solutions are compatible with the regular evolution for these extra quantities. Again, check if this period has and finally do the exact same procedure. In this case, the action for the Einstein scalar Gaston gravity is given by this form, where we have the well-known which is scalar, kinetic term for the scalar field, the potential, and here there is the coupling between the scalar field and the Gaussian invariant. We also consider the matter of Lagrangian. So by varying the action with respect to the metric, we obtain the corresponding modified equations like this in the usual manner. When one varies the action with respect now to the scalar field, we obtain the corresponding for the scalar field, and in this theory, the energy momentum tensor is identical. Now, regarding cosmological assumptions, for the geometry, we assume that the universe is sufficiently large scale, so homogeneous, then reducing and this implies that all quantities in our study only depend on the one. Furthermore, for the case of matter, we assume that it is described by fluid, that is, the energy momentum tensor is given by this form, and we have two components, limiting baryonic matter and then a radiation component with this. Now, by defining this set of dynamical variables, it is possible to construct a dynamical system that in such a way that we have two equations that arise from two modified Friedmann equations. We have one equation that arises from the equation of the previous one. We have three density equations right here: radiation, for matter, and other for curvature, and finally two scalar field equations according to definitions. We also define these auxiliary quantities. Now, the corresponding fixed point sensibility. In order to obtain the fixed points of the theory, we need to explore the case in which the derivatives of all dynamical variables are set to zero. And if one does so, it obtains this table right here. These 5 fixed points. One thing to notice is that we have 4 different behaviors. For the point A, we have radiation dominated solution. Here, for B, we have matter dominated solution. For C, we have an exponentially accelerated solutions. And finally, we have 2 fixed points for curvature dominated solutions, D and E. By exploring the limit with all particular limit for GR, for general relativity, we notice that A, B, C, and D goes to the fixed points of general relativity, while E becomes singular. Alpha tends to 0, then this quantity psi related. Now, in order to perform and to see regarding stability, we considered linear stability theory, and our results suggest that the majority of the fixed points are saddle points, with the first ones, the radiation dominated solutions, being the repellers, and peculiarly enough, point T that is related to the solution can be an attractor or saddle. Only and can be only attractor if alpha and psi satisfy that condition. One particular thing that some of you might have noticed in the meantime is that we have indeed some eigenvalues. And this hints to the fact that linear stability theory may not be enough to describe the stability of such. For now, this paper is under review in Java. So we are still waiting for the reference comments. This is something that in my opinion should stop using simply linear stability theory. One could use, for example, manifold theory in order to evaluate all these eigenvalues that are identical. Just for the sake of completeness, we also considered the same system, but in the general relativity. That is, when the stability, and these are the corresponding fixed points, which are simply the fixed points of the relativity. And this is all to say that indeed, in this limit, we can have the like from radiation domination epoch. Then we can go into a matter domination epoch, and then we end up in sort of dark energy epoch at this stage. So, but now the most important part regarding this work. We have done a dynamical reconstruction of the Lambda CDM model. Okay, Lambda CDM model is a great model. So we will assume these solutions for the potential, for on the matter, and for on the radiation. And of course, this is the corresponding. Okay, so this is nothing new. This is simply Lambda CDM model, the usual one. But now we will be introducing these numerical solutions to the dynamical system, the full one, and check if they are compatible, if these solutions are compatible with the regular equations and for the if they are compatible, then it's perfect. It means that our theory is distinguishable from the Lambda CDM model, at least from the background and evolution. And as you can see, for many different values of the company constant and for two different sets of initial conditions that are compatible with the weak field limits, all the quantities here, theta, psi, and phi, they are regular throughout the entire cosmological evolution. As a result, because it indicates that our model is indeed compatible with the quantum limits. Yeah. So another important aspect since this theory accommodates Lambda CDM-like evolution, it would be interesting to know what is the form of the potential and of the coupling function that satisfies such an evolution. In our case, we had considered these particular initial conditions, but it's not really necessary to these ones. You could vary them in a particular manner. But this is the form of the absolute value of the potential here. As you can see, at late times, that is when phi tends to 1, why 1? Because it's the value of the field at late times. It becomes simply a cosmological constant, while it sort of decays during radiation epoch. For the case of the coupling function, it really depends on the value of alpha. However, the value of alpha times h is unique. It's invariant. Okay, and we pretty much did everything for the case of the potential equal to 0. It's not as interesting as before because in this case, with the potential being equal to 0, the universe, this theory does not have a lifetime cosmic acceleration. So we really need to have the potential in order to trigger the lifetime cosmic acceleration. And yeah, I think it's the main result. So in order to have a late time cosmic exploration, you really need to have the potential. Otherwise, the the coupling with the Gauss-Bonnet is not enough to trigger such a late stage of the universe. So these are my main conclusions. In the cosmological context, this theory admits solutions that are consistent with Planck plate, the weak field solar system dynamics. They are compatible with the solutions for the extra degrees of freedom. Therefore, we have an alternative cosmological model based in a modified gravity theory that is indistinguishable from the standard model of cosmology. In the absence of the potential, the late time cosmic acceleration does not. And this is it. It's really fast because I only have 2 minutes. So thank you very much. And I'm sorry, the beginning was not so great because I was having some issues with my laptop, but I hope you enjoyed.
Any questions?
Yeah. Actually, I was expecting you to put such a question. The thing is, I have been working on dynamical systems quite lately, so for the moment, I'm unable to. Did not compare it, but we plan to do so. But the lambda CDM like evolution in this case is to simply assume that, let me just, yeah, here, it's simply to assume that the potential, the density, the matter density, and the radiation density, they evolve just like in lambda CDM, pretty much like in lambda CDM. These are exactly the lambda CDM solution. Then we just introduce back into the dynamical system and see what happens. It simply as that. But regarding your question about the age data, we plan to do so. Sure. Regarding the geodesic trajectories, as far as I'm concerned, I have, as you know, probably I have been working with minimal geometry. And in these kind of theories, we really have non-conservation of the energy momentum manner. And because of that, we have non-geodesic trajectories. In this case, I am not really sure why we would have precisely because of the covariant conservation of the energy momentum transfer. I think even in this theory, we still have geodesic trajectories. Fine. The scalar could or could not be massless. It depends on the potential. One could define the potential as m squared phi plus some upper interaction. From this expression, one can or cannot say that the silicon is not really dependent.
What is the physics signification of the phoneme?
Um, so I'm not really an expert as far as I'm concerned. These invariants here is in other higher dimensional. Is Gauss phoneme is quite important in the sense that since it's a topological invariant in 4 dimensions, it means that in 4 dimensions equations. And that's the reasons why people tend to use such a scale, because it means that in some way it would masquerade the higher dimensions. And when you move your theory back into the normal 4 dimensions, it does not necessarily appear. I mean, if it appears alone, then it does not contribute to the theory. Why we need to put a scalar field or in order to contribute to the theory. In my opinion, it's important and useful because it can masquerade with higher dimensions when the theory is brought.
Okay, thank you very much.
This is for the this is for the laser point.
Where is it?
So this is the laser. This is the laser.
Please begin. You have 15 minutes.
Can you hear or I think
Excellent.
can you hear me all if I speak without the microphone? Oh, okay. So, hello everyone, my name is Isa. I'm a first year PhD student at UCL. And today I'll talk to you about, I guess, the project that I started, which I'm kind of liking because it's kind of merging what I did with in my master's in Kuwait University with what I'm doing right now at UCL. So I'll talk about a cosmological connection that we found between modifications of quantum mechanics and gravity. So in general, we know that today there are two big theories in physics. We have quantum mechanics on one side describing kind of all matter that we think we understand and describe all the forces except for gravity. And then we have general relativity, a dedicated theory for gravity. And at the same time, we know that this is not the whole story. We know that there is more to know about. There's dark energy, there's dark matter, than 5% of the universe that we understand. And we also know that these theories are not very compatible. And so there have been a lot of attempts to either develop either new models or modify these models to accommodate the experimental results or developments that we are observing. So if I start with general relativity, let me just check. Okay, I made it worse. Okay, so if I start with general relativity, general relativity is our theory of gravity, and it depends on two assumptions: that it's metric compatible and torsion free, and from there we can develop the Einstein-Hilbert action, which depends on the Ricci scalar, and derive the field equations. But as mentioned earlier, this is not really the only way that we can work with gravity. The geometry allows us, the four-dimensional geometry allows us to do much more. So we can actually have torsion, or we can have non-metricity, and among many things that we can do with gravity as well, is that we can have non-linear theories as well. And so one particular model that I work with is we deconstruct the Ricci scalar into a bulk and a boundary. We see that it's only the bulk there that contributes to the field equation, and this develops the set of modified gravity theories which depend on G and not necessarily can be linear in G, so they can have G gravity. And from there, there has been a result in f of G cosmology where Friedmann equation can be written in such a form that I show here at the very bottom, with G equal to minus 6h squared, h squared being the Hubble parameter. And so this modification of gravity leads to a modification of the Friedmann equation. On the other side, from quantum mechanical perspective, we can see something also similar. So if we look at, in quantum mechanics, the standard Heisenberg uncertainty principle, it puts a limit on how we can, or the precision with which we can measure both position and momentum. But it does not put a necessary condition on any single one of them. So as long as you reduce the uncertainty in position and you accommodate for it in momentum, then you really have limitless precision that you can have for each one of them. But quantum gravitational theories do predict or sometimes postulate the existence of a minimum measurable length. And in that case, it's limiting the precision with which we can determine position. And this has in turn led to the modification of the Heisenberg uncertainty principle to what has been famously called now, or generalized uncertainty principle, GUPs, developed more than 30 years ago. This is one of the standard forms of writing the GUP, and it restricts the existence of the uncertainty in momentum squared. The right-hand side really puts an upper limit to how upper limit to the momentum, or the lower limit to the uncertainty in position. And from there, with this modification of the uncertainty principle, we have a modification of the commutation relations to accommodate the uncertainty, and a way to express the position and the momentum operators to satisfy these commutation relations is to keep the position operator the way it is, but expand the momentum operator with P0 actually is the standard canonical momentum operator that satisfies commutation relations. And often alpha 0 here is of interest for the GUP community, which is sometimes called the GUP parameter, and there has been a lot of work to try to determine the value for the GUP parameter, but it's often theoretically assumed to be an order unity, but experimentally it really has a lot of range of values. And so one application for the GUP modifications has been with in cosmology. If we start from the Hamiltonian for an FLRW universe expressed in this form, we can expand the momentum operator here according to our modification with the GUP. And if we do so, then derive the Friedmann equations. This is now the standard Friedmann equations, the standard Friedmann equations, but with the modifications of GUP, we can see that it really has an expanded form of dependence. And this form in particular, now we have those two modifications. We have one side modification stemming from GUP, and we have another slide stemming from modified gravity. It kind of intrigued the question of how we can really work with those two modifications, of how in synchrony or harmony can we have them both together. And so trying to see if we can develop, for example, general form of the Hamiltonian and write an equation of generally a function of the moment, the scale factor, and the momentum. We try to see what kind of modification this will have Friedman equation. And so one trick that we can impose is that if we substitute a variable u that depends on both momentum and scale factor, but try to eliminate the appearance of any one of them explicitly, that what we observe here with the appearance of the scale factor, we see that we can derive the density equal to f of u, and then the h is just 1 over du d rho. And the ability to express both of the expressions this way allows us to use u to eliminate u from the equation, keep it the standard form that we are used to. So we pretty much derive, I guess you cannot see it here very clearly, but this is pretty much just rho equal to a function of the Hubble parameter in general. And so we have a general expression now in this form for the Hubble parameter. And we saw earlier that from modified gravity, we can express the Friedman equation in this form, and we can substitute G for the Hubble parameter. And so if the question was, if we have a general form for the Friedman equations as a function of G, can we derive function of G from that equation? It turns out that we can, according to the formula over here. And so with that, in a way, we have a mechanism going from one way to GUP or modified Heisenberg uncertainty principle. And so this is kind of the mechanism we start working with, and just starting with a simple test. Yeah. So if we start with our usual unmodified FLRT model, then this is the expression of the function of u, f of u, and from there we can derive the equation for rho, for u, and for h squared, and we indeed retrieve the standard form of the Friedman equation. And from there, if we attempt to derive the function of g, we get back just g. And the question is now, what can we do with this? Let's try to apply this technique to the modifications themselves. And immediately we start seeing some interesting results. So, for example, if we just do a simple modification where we introduce a linear term for the function of u, then we see that we get a result that adds a constant term to the Friedman equations, and the same with the Roger model. And so, if we do now another modification where we add a constant, we see that we indeed get the same result again. We see that the constant appears, and we started thinking, well, is there an underlying relation? It turns out, in fact, there is. It turns out that a function of f of u of this form will always lead to the introduction of constant equations. This is something that kind of isn't obvious, I guess, that when we work with from FLRW model, you wouldn't think that deconstructing or writing the momentum terms in this expression will lead to modification in this way. So, and just, I guess that was a comment of interest, that but having a constant term in the Friedman equations, and which is kind of related, I guess, to the cosmological constant, what kind of relation that we can develop this way? I don't have an answer to this question, I guess I'm just posing it over here. But in a way, it allows us also to see if we can find a relation between GUP parameter. And while this is a simple modification that gave a nice result, we tried to test it with many different models, but the results are often giving us very complicated equations. So one example that I show as well is the loop quantum cosmology example. So in loop quantum cosmology, this is the standard form of representing the Friedman equation with a linear term and a quadratic term as well. And when we derive the Friedman equations from the f of u model from there, we have this sine squared result appearing. And remember, this is in the Hamiltonian, so we have kind of a sine squared of the momentum of the sphere Hamiltonian, which is something, I guess it's kind of strange. Of course, in the limit of large alpha, we get back our usual result, but a sine squared isn't something I guess usually think of as they do this kind of modification, especially from the quantum mechanical perspective. When we take it to f of g, we get something even very complex. So if you're working on f of g models and trying to modify them, this wouldn't be the kind of modification that one would expect to see, but this is the kind of modification that one sees when we compare to the f of g model from this derivation. And so I guess I will summarize at this point. My main point here is that we do have these two areas that people usually modify the equations from. From quantum mechanical perspective, we have those GUP modifications appealing to the Heisenberg uncertainty principle. And from modified gravity, we have interesting work with modifications to the general relativity. But these modifications as well entitled modifications to the Friedman equation, but we can really have this connection between them. And what looks very nice in one model might not look very nice in the other model. So I guess this is my main point, is that what kind of insight we can get from such a mechanism we can use to get lessons, or what can we learn about how we verify these models. Thank you very much. These are the two papers.
Any questions?
I just wondered, you're aware of what without introducing one. If you do that,
You mean like introducing new methodology of keeping?
I mean, using the EUV, so the generalization, and so they will feed into your cosmological.
Yeah, I mean, I think I understand the question. I'm not sure how exactly how would that appear in the, how would that modify the, yeah.
I just have to make sure what
I guess that's true. I mean, in general, it's very common to modify the. So in that case, that makes sense. But as you said, like there's another way. I haven't tested that. How would that work?
Thank you very much. Oh, Michelle, oh, 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 group U1X. It's not, in general case, must be group of standard model. It can be some field of the early universe. Despite the fact that magnetic field of early universe is contained only inside the topological defect, it can affect on the vacuum of the matter field due to Aharonov-Bohm effect. The conditions of NMBGT of condensate field leads to continuization of the vortex flux inside the topological defect. For contingent matter fields that interact with the gauge field of the group U1X, with coupling constant A tilde, the field solutions will be determined by some parameter. Then can be H integer and non-integer. And the vacuum in the presence of topological defect polarized, and it leads to a vacuum current around the cosmic string and vacuum polarization. It can be, in principle, observed. Let's suppose that our standard model particles have a small charge under the group, magnetic group, and have a charge to the new field U1X. Then the induced vacuum current will produce the real magnetic field around the cosmic string and can be some physical model. We will consider this task in the model of impenetrable impenetrable tube for matter. And that we will think that magnetic flux will be only inside. And on the surface of the tubes, we will impose some boundary condition. In the classical theory, the magnetic field inside the tube does not act on matter outside the tube. But in quantum physics, we know the Aharonov-Bohm effect, and magnetic field inside the tube can act on the matter outside the tube. Also, the boundary conditions imposed on the tube change wave function solution and induce different quantum numbers in the vacuum outside, such as energy density, current, magnetic flux. This effect is called as Casimir-Aharonov-Bohm effect. Realization in nature. You know, the well-known example is Abrikosov vortex in superconductors of the second kind. The magnetic cosmic strings in cosmology, and even a discontinuity on the surface of sheet of graphene. And now about dependence of the induced total vacuum energy of the scalar field on the coupling to space-time curvature in flat space. Some general definition, we consider scalar field this interaction with space-time curvature. It derives equation of motion that contains parameter C, and define energy momentum tensors that also contains parameter C. But it's interesting, it is well-known fact, then in flat space-time, when R is zero, the dependence on parameter C remains. So vacuum energy momentum tensor will depend on some unknown parameter. From theoretical point, there are some distinguished values. Its values at first, d minus 1 by 4d is at this value, this theory becomes conformally invariant. At value as c is 1 plus, we will have the canonical definition of momentum tensor. And at c is 0, we get the minimal coupling with space-time curvature. Okay, we will think that our covariant derivative contain only one non-Venetian component, where phi is angle in the polar coordinates. With this definition, we get magnetic loop inside the tube. And the complex physics we are known the physics of the universe, of the early universe, but we think that complex physics implies topological defects can be modeled with boundary conditions on the tube surface. And the crucial question concerns the boundary condition imposed on the matter field on the tube's edge. We will consider a most general case of Robin type boundary condition. It is one parametrical boundary condition that is defined by parameter theta. And there are two distinguished cases. The theta there corresponds to the reflex boundary condition, and the theta p by 2 corresponds to Neyman boundary. The boundary conditions are not artificial, they are widely used in physics, in head conduction, in electrostatics, in continuum mechanics, and we also will consider the Robin boundary conditions. One particle solution is quite complex. In this case, it's solution of Klein-Gordon equation. We can write general relation for induced in vacuum energy in general d plus 1 space-time. And we see path depending on parameters. The function g is very complex function. It defines through the one particle solutions. And we made a renormalization by subtracting the energy density in the absence of magnetic flux inside the tube. Due to infinite limits of summation, the effect will depend only on the fractional part of the magnetic flux inside the tube. Okay. The relation for induced energy in 2 plus 1 space-time is quite simple. And they can be presented as some function plus path that depend on parameters. This function was built only by numerical methods. And we saw that function alpha tilde is not zero. The energy, the induced energy, more correctly, the induced energy density, depends on parameter C. It's a well-known fact. It was known a long time ago. As example of the induced energy density in 2 plus 1 space-time as function of different values of parameters. As you see, there is quite a difficult structure at different values of parameters. What the parameter is realized in the nature, we don't know. The question is, will the total induced vacuum energy, not energy density, but full energy, will it depend on the parameter C or not? It's our definition of full energy. We simply integrate the energy density over the spatial coordinate, and we'll be interested in the second step. Is it zero or is it not zero? Our numerical calculations shows the following result. It's not zero. Or more strictly, at theta 0, we have zero values of parameter E. And that case, parameter C, the parameter theta minus P naught. In other words, in the case of Dirichlet boundary conditions, the full induced energy does not depend on parameter C. But in general case of Robin boundary condition, the induced vacuum energy will depend on parameter C. It's result for case of the 2 plus 1 space-time. We can also calculate more interesting physical case in the space of 3 plus 1. And we see that induced vacuum dimensionless energy is sufficiently stronger than in 2 plus 1 space-time. And it was interesting for us to consider the case of 4 plus 1 space-time. And we also see that induced vacuum dimensionless energy is sufficiently stronger than in 3 plus 1 times. And conclusions. We see that in the vacuum of charged massive scalar field, energy is induced in the presence of topological defect. The effect is periodic of the magnetic flux of the tube with a period equal to London magnetic flux. The effect is greater the smaller the thickness of the tube, and for a tube of big radius, the vacuum effects can be negative. In the case of Dirichlet-Neyman boundary conditions, the total induced vacuum energy does not depend on the parameter of coupling to phase cavity, but in general case of Robin boundary condition, it does. And induced vacuum dimensionless energy is increasing with increasing space-time dimension. Thank you for your attention. In our case, vacuum energy is induced in the vicinity of this topological defect. And it very quickly decreases as we will go away. But in fact, we show that this induced vacuum energy is dependent from parameter of coupling to cavity. And in principle, it's one of to consider the theoretical prediction. Okay, thank you.
Yes, this is
Yes,
mine.
yes. Oh, thank you for your question.
Yes. Where is the? Oh, here.
Yes, so hello everyone. My name is Merrick Wozni. I'm from the University of Babeș-Bolyai, and I'll be giving a talk on the Hergo's principle within an f of RT gravity. So just a brief overview of what I'll be talking about. First, I'll introduce the Hergo's principle. I'll motivate it with some dissipative dynamics. Then I'll give a brief application to general relativity. And then for the main point, I'll be generalizing it to f of RT gravity. And finally, I'll discuss some cosmological applications and give a brief summary. Okay, so what exactly is the Hergo's variational principle? Well, it's motivated by the fact that the most general Lagrangian that you should be able to have should actually depend on the action itself, since it is, after all, a scalar quantity. And then it was initially derived in the 1930s as a way to describe dissipative dynamics. On the next slide, we'll see a prime example of this and how it works in action. But just to get to the main principle itself, this is, excuse me, this is how its setup looks. It looks very, very similar to the usual Euler-Lagrange setup that you would have, your principle of stationary action. However, the only difference being that your Lagrangian now depends on the action S. So what happens when you actually go through and you do the derivation, you do the variation of this principle, you'll end up with the so-called general Euler-Lagrange equations. They look very similar to the regular Euler-Lagrange equations, the only difference being this middle term here, where you have your Lagrangian with respect to the action, and of course your canonical momentum term. So this term that I just talked about, it's usually denoted by gamma, and that's because it's associated with dissipative terms. And of course, when this term is equal to 0, we get back our regular Euler-Lagrange equation. So to just get a feel for how this principle works, we can just discuss a very simple example. We can talk about a particle with mass m, subject to some potential u, and it's subject to some damping force proportional to a constant, right? So we have our typical Lagrangian here, kinetic energy, potential energy, and then of course, where we're going to get our dissipation from our term that's proportional to the action. So when we plug this Lagrangian into the generalized Lagrange equations, we'll actually get this equation of motion right here. And you'll see that the novelty here is that we now have a term proportional to the first derivative. And that is coming from our dissipation term proportional to the action. And this models very well non-conservative systems, in particular, a prime example being the damped harmonic oscillator. And now you might ask, well, why is this important? We can arrive at this equation of motion in a regular Euler-Lagrange perspective. And I'd say, well, we can only do that with explicit time dependence. And where the Hergold's principle really shines is that in this formalism, we still have a physical Hamiltonian. And I say physical Hamiltonian in the sense that it's the sum of all the energy. So we have our usual definition here, and we have our kinetic potential and our dissipative energy. So we can also apply this to general relativity. Everything gets upgraded in a very straightforward way. Our system setup here is almost exactly the same as the particle perspective, except it's covariantly updated. So instead of a time derivative of the action, we have our covariant derivative of something we're going to introduce called the action density. And again, that's just to make things generally covariant. But again, on the right-hand side, we have our regular Lagrangian. And in the case of general relativity, we'll have our GR Lagrangian plus our dissipation term here. We're going to couple it to the action density, some arbitrary vector fields, and we're going to call that the Hergold's vector. So after we take this variation of our Lagrangian, and just a little note that our second equation here is just, it's really just there to ensure all our boundary conditions are being satisfied the way we want them to. But when we take a variation, we end up with this field equation here. And it looks very much like the regular general relativity field equation. We have our Einstein tensor, we have our usual energy momentum tensor, but the new term here is going to be this K tensor, and this is where all the dissipation is going to come from. And it's written out explicitly. It just depends on some covariant derivatives of our Hergold's vector, as well as some coupling terms here. And for anyone that's interested, I won't be getting too much detail here, but you can do this formalism in a more general way by using differential forms. But since I'll be talking about gravity, we'll keep it in a metric sense. Okay, now to get to the main point, I want to generalize this Herglotz principle to f of RT gravity. And if you're not familiar with f of RT gravity, really all it does is upgrade general relativity by replacing the Ricci scalar r with an arbitrary function of the Ricci scalar and the trace of the energy momentum tensor. So when we take the variation within the Herglotz principle, we end up with the field equations here. They look very similar to the usual f of RT equations from the general Lagrangian variation. Again, with the only difference being this h mu nu tensor. We're going to call that the Herglotz tensor, and explicitly written out, it's a combination of the k tensor from the previous slide, along with some interaction terms with your f of r and your Herglotz vector. And just a couple comments. Again, if anyone's unfamiliar with f of RT gravity, the subscripts on the function f here are just denoting partial derivatives with respect to that with that variable. And then we have our theta tensor here. It's really just some sort of variation with respect to the energy momentum tensor. And then two more comments that are in order. In the case of vanishing Herglotz fields, we have our usual equations of f of RT gravity. And when f of RT is equal to r, we have our h equal to k, and we get back the equations we had on the previous slide. Everything works out in the limits that we want them to. And so what can we do with this field equation now that we have it? And one of the first things we can talk about is energy momentum conservation. But in order to do that, we need to explicitly write out our theta tensor. We're going to expand it to first order. Of course, you can do second order, third order, and so on. But first order is fine just for this talk. And when you take the divergence, both sides of your field equation, this is what you'll end up with here. You can see it's quite long. You might see some parallels with regular f of RT gravity. In general, this is not conserved. This has been interpreted in a variety of different ways, just one of them being particle production of open systems. But there is one main difference that I want to point out here that goes away from general f of RT gravity theory. And that's going to be that we have additional degrees of freedom from our Herglotz vector. And what this enables us to do is to retain energy conservation just by applying this constraint here to the Herglotz field. So once we say that this constraint must happen, then we're guaranteed to have energy momentum conservation. So the upshot of this being within f of RT gravity, yes, we can have conserved theories. However, it requires us to have a very specific choice of our function f. However, with the Herglotz variational principle, we're able to create a much more general choice and choose many more f of RT functions. So what can we do after talking about conservation? Well, of course, we can talk about cosmology. We're going to consider your very basic setup, flat FRLW metric, perfect fluid energy momentum tensor, and just a couple of things to note. Because of the homogeneity and isotropy of our spacetime, all of our scalar functions will only depend on the co-moving time. And in particular, our Herglotz vector will only be the time component of some scalar field. So that leads me to the generalized Friedmann equations. I've written them here in an effective field form, so that way you can see the deviation from the usual general relativity equations. And just one thing to note, that we only have two equations here, and we do have 5 unknown parameters. So we do need 3 additional constraints to form our closed system, with one of those constraints being our actual choice of function f of RT. So let's do that now. Let's choose a functional form. I'm going to choose the most simple example, r plus alpha t. And hopefully in a couple slides time, you'll see why I've chosen this specific function. Our other 2 constraints are going to be a pressureless fluid, so p equal to 0, and an effective equation of state for our pressure and density. we'll work in dimensionless coordinates just to make the equations a bit easier to read. And this is the resulting system of equations after you plug it into the field equation. And before I talk about the solution to this, I want to talk about the case of standard f of RT gravity without the Herglotz principle. So in regular f of RT gravity, we only have one dynamical generalized FRW equation, and we can write down the solution to this almost immediately. We can write down the Hubble function and the scale factor, how they evolve in time. And I put this here explicitly because this model is known to not do a good job of explaining the data or fitting to lambda CDM very well. And in particular, that's because the deceleration parameter for this model, it's just a constant. So it can't account for a transition from decelerating to accelerating universe. But we'll see how the Herglotz field is actually able to fix this. So in order to make an apt comparison with data, we'll move into a redshift representation. And so the system of equations I just showed just a second ago, in a redshift representation, take this explicit form here. So they're two coupled nonlinear equations, and we'll solve these numerically actually in an MC-MC analysis for our free parameters A and W. And just for consistency, I've also written here the solution for the non-Herglotz principle FRW equation. So again, just a very standard MC-MC analysis on our system of equations, numerically solved. Here we consider the CC, supernovae, BAO, and R22 data sets. Again, just for consistency, we do the same exact thing without the Herglotz principle. And now we can compare the two. So comparing the two, on the right-hand plot, we see immediately that for the Herglotz variational model, we no longer have a constant deceleration parameter. So now we're able to account for that decelerating to accelerating phase in the universe. And on the plot on the left-hand side, you can see that when we apply the Herglotz variational principle instead of the regular principle, our function, our Hubble function here fits much better to the data and is much closely resembles the lambda CDM model. Again, that's easier seen in our difference plot here for the Hubble function. We also have some other parameters such as the jerk, the snap, and the ONZ diagnostic. So you can see that even though it looks very much like the lambda CDM in the difference, there is still some work that could be further done to talk about the differences in these other parameters, since it does kind of deviate away from lambda CDM. So that brings me just to a final conclusion, just to wrap up what we talked about. So I introduced the Herglotz variational principle. It was motivated by dissipative dynamics in those very easy point particle descriptions. We applied the Herglotz variational principle to f of RT gravity. And here I really want to stress that the Herglotz variational principle is something on its own. It doesn't have to be applied to a modified gravity theory. It can be applied to anything just like general relativity. But here we did apply it to a modified gravity theory. We found the field equations, we found the energy momentum tensor divergence, and in particular, in that case, we found that we were able to create a much more general conservative theory after using the Herglotz variational principle. Then we computed the Friedmann equations for a specific choice of f of RT. We used some MC-MC analysis to compare the Herglotz and non-Herglotz models. And in the end, we found that the Herglotz formalism did a much better job, a much more consistent job of comparing with observed data and with lambda CDM than your standard f of RT gravity formulation. But we still have some open challenges. I'd say the main one being a physical interpretation of the Herglotz field, and then of course some other ones being thermodynamics of your cosmological models. And that's it. Thank you very much. Yeah, so in the kind of upgraded form, field formalism, instead of the action, it's an action density. And if you want to compare the Lagrange using here, is your standard GR Lagrange plus this. So, again, this is just an arbitrary trick that you can use to couple it. Because if you didn't have some term proportional to the action density, you would just get back to the regular GR. As you can see, like with this very simple example, we have our term proportional to the actual action. So if we want to modify general relativity in some way, we have to, again, add some term proportional to the action density. And the easiest possible way to do that is just to couple it with some vector. Sorry?
Should we understand?
No, the small s is analogous to the actual general action. That it doesn't matter what your Lagrangian is, it just matters that it's the action of the Lagrangian. Like I said, it is something we work on, but if you're asking me personally what I think, um, it is a tough question to answer. I think maybe um, it could have something to do with dark energy in the sense that fluid propagating that moment or something along these lines, but it is something that would require a lot more conceptual. Correct. Right. And but again, the problem is what is the actual physical interpretation of that field may not be straightforward as just no. Yeah, yeah, it doesn't have on-shell dynamics.
Well, thank you. Hello, everyone. I'm here to present our work entitled by Preheating and Gravitational Waves Production in Hybrid Metric Palatini Approach. So my talk is organized as follows. Introduction, Higgs Hybrid Metric Palatini Model, constraints on preheating, gravitational waves production during preheating, and summary and conclusion. So, as we know, inflation has become fundamental paradigm to study early universe, not only because it solves problems of standard cosmological model, but also it provides explanation for primordial fluctuations that that are seeds for a large structure we observe today in the universe. On the other hand, standard cosmological model doesn't address some issues, especially about the late accelerated expansion of the universe and also the existence of singularities. So this is why we need to modify gravity to be consistent with observations. To do so, we can consider two formalisms, metric and Palatini approaches. The first, another approach has become popular recently, in which we can combine elements from both original formalisms, and it is known as hybrid metric Palatini approach. So our model is described by this action. It contains three terms. The first one is the Heisenstein term. The second is Palatini curvature non-minimally coupled to scalar field. And the third one is the density Lagrangian indicating the energy and mass in the universe. So from this action, we can write this action, and with respect to the metric, the scalar field, and the connection, we can derive these three fundamental equations. The first is the reduced, the modified Einstein field equations that relates the geometry to the content of the universe and describe how influence each other. The second is the Klein order equation that describe the evolution of behavior of scalar field, and second is equation of motion, as we see here. So from Einstein field equations, we can derive the modified statement equation as follows. We can also adopt slower approximation to simplify this complicated equation and get this reduced one. We calculated in the next step. We calculate the main inflationary parameters. First one is the number of epochs. It tells us how the universe expands during inflation. Second is the spectral index, characterizing the distribution of density fluctuation, and third is the ratio of tensor to scalar perturbation. So to check the reliability of our model, we consider Higgs field with this quartic potential to play the role of inflation. We plot here in this figure, we plot the spectral index as a function of number of epochs. We consider three values of coupling constant, G. So as we can see here, all three curves cross this gray region caused by observational data. The second figure represents the ratio, the tensor to scalar ratio as function of spectral index, including these contours of confidence. So here we have for she is equal to 10 minus 3.9 and she equal to 10 power minus 4.1. So in these two cases, curves cross this 1 sigma contour. So we can see that our model is in agreement with observation. So the second part of my talk is about preheating. In fact, after the inflation, the universe is left cold and quasi-empty of matter. This is why we need transition phase between inflation and radiation dominated. This phase is known as reheating, during which the energy stored in the Platon field is converted to particles, thermalizing the universe. However, this process of reheating is too slow and may not be efficient to lead to quick transfer of energy. So we introduce preheating as initial phase of reheating, during which the is characterized by parametric resonance that lead to quick that lead to explosive and rapid production of particles. So to study preheating phase, we face a problem of lack of observational data. So as a solution, in our study, we relate preheating phase to reheating and inflationary phase. This equation describes the process of the universe through different epochs, introducing different number of. We also assume that this relation that relates the energy density at the end of inflation and the energy density at the end of preheating, where this parameter delta indicate the efficiency of preheating process. In this figure, we have the evolution of homogeneous ham through different, as a function of scale factor, through different periods from the horizon crossing to the present time. In this equation, we express preheating duration given by the number of epochs of preheating in terms of preheating and inflationary parameters such as number of efforts and the heating duration, given as a function of thermalization temperature by this following equation. So here we plot our results. We plot the preheating duration as a function of spectral index for different values of equation of states, and for two specific values of coupling constant. So we observe here that all curves cross this observation bounds imposed on the spectral index by Planck data. The same thing here with different value of delta, parameter delta. So we see that all curves cross this bound. Now let's discuss the third part of this talk, which is gravitational waves production. So as I have mentioned before, preheating phase can lead to rapid and explosive production of particles. This can induce significant metric fluctuations and inhomogeneities. This can generate gravitational waves and primordial black holes. These gravitational waves are ripples of space-time itself and can propagate at the speed of light. So it can provide more information about the early universe. In our study, we focus on the current power spectrum of gravitational wave energy density defined by this equation, from which we can derive this expression where we express omega 0 as a function of different inflationary parameters. Here we plot omega 0 as a function of preheating duration, considering different values of energy density spectrum. We can see here that our results are in good agreement with observation, as omega 0 remains in the cloud region for appropriate range of preheating duration. We also plot omega 0 as a function of the spectral index. So here we can see that for she equal to 10 power minus 4.1, the results are consistent with observation, as all curves cross this bound, but not for she equal to 10 power minus 3.9. Here we study the spectrum of gravitational waves energy density as a function of frequency. So we use this equation, and we plot these two figures for two specific values of delta equation of space. Here we consider omega equal to quarter, and here we consider omega equal to 0. So we observe that for this case, where omega equal to quarter, all curves corresponding to different free values of preheating duration is cross this sensitivity curves, but not the case with omega equal to 0. So to summarize what we have seen in this talk, we have studied the hybrid metric Palatine inflationary model with Higgs field. We have set constraints on preheating phase using observational data imposed on the inflationary parameters. We have also investigated the production of gravitational waves during preheating phase. And as a conclusion, we conclude that our model can explain the preheating phase and also the production of gravitational waves, and also these inter-gravitational waves can be used to test the inflationary models. Thank you very much.
What can you say about renewable energy that is major?
Thank you for your question. To be honest, I didn't yet study in this. Sorry? Why? We use XP? Yeah. We use XP because it is only scalar experimental.
Okay, thank you very much.
Good evening. My name is Theodora Matei, and today I will present for the last presentation of our work regarding constraining with the Big Bang nucleosynthesis theory the cosmological evolution of a warm inflationary universe with a Weyl boundary. The presentation is structured as follows. First, I will begin by presenting the theoretical framework around with the motivation for considering a Weyl integrable geometry within warm inflation. Following, I will I will describe the methodology used along with the cosmological evolution that was constrained with the Big Bang nucleosynthesis theory and the computational approach. And finally, I will show the results that we obtained, and I will sum up. So moving on to the first section. Inflation presents a successful framework for describing the homogeneity and isotropy of space by introducing a scalar field whose energy density must briefly dominate the energy of the universe at its early beginnings. From Alan Gould's inflationary universe, various models were proposed in which a cold and rapid expansion took place. However, in such scenarios, a reheating mechanism is always needed in order to transfer the energy from the inflaton field to the standard model particles at the end of the inflationary regime. In contrary, warm inflation presents an alternative as the scalar field is allowed to interact dynamically with other fields through dissipative interactions that are captured by the balance equation. The scalar field evolves through the dissipative Klein-Gordon equation, and therefore can both describe the creation of space and the creation of particles at the same time. This current investigation is meant to extend a previous work developed in 2024, in which such a warm inflationary regime was considered to have an initial boundary, and in which the radiation component follows an increase, a standard increase towards a maximum value, followed by a decrease due to the fact that the expansion factor will be much greater than the particle creation rate due to this accelerated decay of the scalar field. We consider that the initial universe had a boundary which can be described by considering the action, which is an invariant under conformal. By using an integrable non-metricity condition, we can describe the Weyl vector field and the divergence of another scalar field, psi, which accounts for the boundary influence. The gravitational action can be rewritten in this regard with the Ricci scalar that is rewritten in a Weylian formalism. And within the previous work, we derived the which will have an additional term coming from the inflaton field and the supplementary boundary terms coming from the vector. By applying this to the Friedmann-Dimensional-Walker metric, we arrived at the Friedmann equations that are modified to include an additional energy density and pressure, which actually contain the additional two scalar fields, the inflaton and the boundary terms, in the evolution of the universe. The conservation equation for these terms can be further split into three distinct scenarios. One in which the radiation component arises due to both the decay of the scalar field, the and the boundary terms. A second model actually equivalent to the standard warm inflationary scenario because the scalar field, the inflaton field only drives the radiation component creation, and the third model proposes that this radiation component a direct effect of the Weyl boundary terms. We furthermore study the influence of various scalar potential fields. For example, we tried to how this evolution, how this cosmological will be consistent with the BBN by considering the null potential tree, quadratic high potential, the mixed high potential, and an exponential. So within this current investigation, we try to estimate these scalar potential fields by applying the Big Bang nucleosynthesis constraints that will be described in this current section. So initially, the universe was filled with primordial plasma, which had various contributors that that were in thermal equilibrium, as their interaction rate was much greater than the expansion of the universe. As the universe expanded and cooled, this reaction rate dropped below the Hubble expansion factor, and therefore a freeze-out will occur, in which particles decouple from this primordial plasma and leave behind the Rayleigh density of non-electric. Furthermore, will be traced in the further on detected abundances of elements. An increase in the Hubble function will, for example, lead to an earlier decoupling, and thus more of these abundances will be detected after the BBN ends. So the additional contribution from the two scalar fields introduced a shift in the standard Hubble function, and therefore as the Hubble function is related to the freeze-out temperature, we can impose an upper bound on these additional components based on the relationship between the helium-4 mass fraction and the freeze-out temperature. This upper bound is imposed throughout our analysis, and to impose it, we use the primordial software package, which is a Python code that calculates the BBN abundances by using the thermonuclear rates of by the NACRE2 database. So to the standard plasma sector, we just add the contributions from the boundary and the inflaton field, and we can just recalculate the thermal background of in this code. And to do so, we developed Genesis, which is a two-stage program that has two main functionalities. One that uses a genetic algorithm to search for the initial values that satisfy the cosmological equations, this system of the three scenarios I previously talked about, and then an MCMC process effectively is used to estimate the scalar potential parameters. The first stage is used because we want to reduce the number of parameters, and this is done in the null potential case, and the process will further end goal to find the distribution of the posterior distributions of the scalar potential parameters. The genetic algorithm evolves a set of initial parameter values and ranks them based on their ability to satisfy the BBN condition, and that they should have the equation in a well-established bounds. A crossover and mutation are also applied. This is an optimization algorithm. A crossover works in the following way. A random point along two sets of best fit parameters is chosen, and the parameters therefore swapped in order to include diversity into the system, and the mutation is applied by assigning a random value to in order to escape local minima if encountered. The results that come from the genetic algorithm, so the initial values for the system of equations become fixed parameters in primordial, and therefore we can compute the energy density in terms of their temperature dependence as the primordial package requires, And further on, the Hubble function can be reevaluated, and by further describing the nuclear reaction structure, we get to modify the abundances for the light element. So we then perform the Bayesian estimation process, in which we consider the following chi-square function in order to ensure the convergence of the chain. For the observational constraints, we use the recommendations given by the particle group. We use priors from a uniform distribution to ensure that our chains converge, and we use the MC sampling method. And now on to the results of our analysis. Here are represented the posterior distribution of each figure represents the scalar potential class. So here depicted the quadratic potential, here the fixed potential, and the exponential one. The gray shaded area here represents the first cosmological model in which both scalar fields contributed to the creation of. And you can observe that for the first model in the Higgs, the chains converge towards a higher value than the other two, even though if we all the predictions of this analysis at the estimation region. Moreover, what's interesting is that the red shaded area, which represents the standard worm inflationary evolution for the radiation, and the blue shaded area, which represents the wire-driven radiation evolution. They both converge in the same regions, meaning that the while contribution for the radiation production can in fact describe the standard inflationary prediction. In terms of the primordial elements, with model. So this is the first model, the second, and the third model, and here are represented the three PBN abundances that for abundance, deuterium and helium-3 abundance, and we can see that across models the correlation between the consistent across all models, and it can be seen here, but we can make it actually underfits the data, which is given by the other two in red. But if we consider the Akaiyan Bayesian information criteria, we can see that this model is not rejected, and in fact, neither of the model is rejected. Moreover, what can be inferred from this statistical analysis is that the exponential type potential seems to describe the best the BBN abundances across all models. So even though we have models that seem to be the best, the exponential one actually performed the best across all inflation, in all cosmological evolution. So to sum up, this analysis extended the previous work in which and we imposed some BBN constraints on the evolution of the energy density of scalar fields, the inflation and the boundary terms that further on were considered within the Genesis program, which was developed by us, with two main functionalities. One in which a genetic algorithm is used in order to find the initial values for the system of equations, and then an LCMC approach tries to estimate the scalar potential for all three models. We conclude that that all models describe well the standard BBN abundances, and moreover, we can say that the boundary terms may actually viable mechanism that is supported by the BBN data. Thank you very much for your attention. This analysis was conducted for the BGN. Maybe a further analysis can be conducted. So within this study, only the BGN. Yeah, yeah. We won't have to.